All right, so we're looking at some questions today, and then we are going to be focusing on these two questions so I can get a basic grasp of how to use the formulas we have talked about earlier. And for the first question, it said a mixture with an enantiometric excess of 40% R has what composition of enantiomers? So I'm going to be dropping a formula that I've not dropped yet so that you see how to solve this particular question. So when you're looking for the dextrorotatory isomer, you want to know the percentage present because it said what composition of enantiomers are present here. So the percentage present for the dextrorotatory isomer is equal to, in open brackets, 100 plus enantiometric excess divided by 2. 100 plus enantiometric excess divided by 2. Then when you are looking for the negative isomer, the amount of negative isomer, that's the level rotatory present, how you solve for that is 100 minus enantiometric excess divided by 2. So let us solve it now. So we already have 40% of R. So let us see, since R, we have 40% of R, it simply means that R is the one that is in excess. So for us to be able to know the amount of R present, we are going to solve now. So for the R, the percentage present for R will now be equal to 100 plus 40, because that's the enantiometric excess, 40%, divided by 2. 100 plus 40 is 140, divided by 2, that's going to give us 70. So it means that the amount of R we have here is 70% of R. Then what about if we have R already, what we'll now be looking for now is the amount of S present. You can decide that you want to do 100 minus 70 to get the amount of S present, or you could decide to use this formula. So 100 minus 70 will give us 30, but let's use this formula so you can see that the formula indeed is working. So the percentage present of X is equal to 100 minus 40 divided by 2. 100 minus 40 is going to give you 60, and 60 divided by 2 is going to give you 30%. So you can see that any which way you decide to go, you'll still get 70% of R and 30% of S. 70 minus 30 is going to give you back the enantiometric essence, which is 40% of R. So number one question, the composition is 70% of R and then 30% of S. So I'm going to progress to the second question. But the second question says morphine. Morphine has a specific rotation of minus 132 degrees. That means it is level rotatory, specific rotation. Now, if a student uses a sample that has a concentration of 0.0128 gram per mole and in a polarimeter of path length of 1 dm, that means it's a standard polarimeter, what would the student expect the observed rotation to be? So the thing we have to do quickly is for us to write down our formula. So the observed rotation we already know is equal to specific rotation times path length times concentration. So the specific rotation, according to our question, is minus 132 degrees Celsius. So that's minus 132 degrees, not Celsius, please. There's no Celsius, just the degrees. Celsius is for temperature. So minus 132 degrees. Then we are going to be multiplying by the path length. According to this, we have a path length of what? 1 decimeter. So our path length is 1. And then according to the question, we have a concentration of morphine of 0.0128 gram per mole. So what we have here is 0.0128 gram per mole. So minus 132, if you press your calculator, times 1 is going to give you minus 132. Then when you multiply by 0.0128, you're going to have minus 1.69 degrees. So the implication is that the observed rotation for morphine concentration of 0.0128 gram per mole in a polarimeter that is 1 dm, even if morphine specific rotation is minus 132 degrees, is actually minus 1.69 degrees. So that is the observed rotation. So we can now move on to talk more about chirality. Now, when we talk about a chiral substance or chiral object, I've talked about it before. We're talking about an object that has a mirror image that is non superimposable. Non-superimposable. Now, every object has a mirror image, but the question is the mirror image superimposable on the object or is it not superimposable? Now, most of the objects we know, for example, objects like football, for example, is always superimposable on this mirror image. But there are some objects like the human hand. Now, the human hand we have here, this is my right hand, this is my left hand. Now, this is like a mirror image of this, and it's like a mirror image of this. But look at this. It is not exactly the same. Where this one is not where this particular one is. Like the whole of my right hand, no matter how hard I try, can never be superimposed on this particular hand. So the implication is that what we have here are images, mirror images that are non-superimposable. So you call such objects chiral objects. So but the objects that have like that the mirror image can be superimposed on itself is referred to as a chiral object. So I'm going to be writing that down. So we have chiral. Chiral is when it is non-superimposable. Then achiral is when the image is superimposable. So when the image is superimposable, then we have an achiral object. So optical rotation only takes place in chiral object. Optical rotation does not occur in a chiral object. Another thing again you have to take note of is the fact that even if we have an object that has a mirror image that is not superimposable, if two of them are in same exact amount, we refer to such a mixture, I've said it before, as a racemic mixture. And a racemic mixture will not have any observed rotation. The reason is because while one rotates it to a particular degree to the right, the other enantiomer is going to rotate it to the other degree to the left. And like another important information, like I mentioned before, is that the mirror image of one compound that is not superimposable on the other compound is referred to as enantiomer. It's referred to as enantiomer. You could also call it optical isomer. You could also call it optical isomer. So I'm going to be giving an example with lactic acid, and then I'll show you exactly what we're talking about. So let's draw the structure of lactic acid. So this is a carbon here, and then let's say we have a hydrogen here, and then we have an OH group here, and then we have a COOH group here, then we have H3C group here. Now this is the structure of a lactic acid. Now this acid, let's assume that what we have here is a mirror. Let's assume that what we have here is a mirror. So I want to draw the mirror image of this. So we're going to have something like this. So this is going to be our H. Then we're going to have this our C. So we're going to be having OH here. Then we're going to be having COOH here. And then we're going to be having CH3 here. So this is the mirror image of this. Now, just so that you're able to see what this looks like, if we're looking at it in this dimension, what you simply do is that you flip it 180 degrees. I've mentioned that before. Flip it 180 degrees and then change either the constituent of the hash and wedge bond, or you change the bond while leaving the constituents where they are. So what I simply mean is that when you move it 180 degrees, you're going to have the C this way. You're going to be having our COOH here, and we're going to be having our H3C here. But then we're going to be working with changing our bond instead of changing the constituents. We will learn about that as we make progress more better. I've highlighted it before and I'm going back to it again. So we are going to be changing the let's take the bond away. Let's just change the substituents. So the hash bond now, where we have hydrogen, we're not going to put OH, and then where we have OH initially, we're now going to be putting our hydrogen. So this image here This image here is this particular image here. So the only thing is that I try to present it the way this other one is. Now you can see for yourself now, initially this OH was at the front projecting outward while the H was projecting backward, but in the mirror image the OH is now projecting backward and the H is now projecting forward. So if you put this on this, they are not exactly the same, because while in this one OH is coming forward, in this one the OH is going backward, and same with hydrogen. So this is the mirror image of lactic acid, and because the two images are non-superimposable, you can simply say that lactic acid is chiral. You can simply say that lactic acid is chiral. Now let's talk about propanoic acid. Now propanoic acid, instead of having an OH here, you're going to have just hydrogen. So when you flip it, what you're also going to have here is hydrogen. And then when you flip it and then work on the bonds, what you're still going to be having here is going to be what? Hydrogen. So in this particular place, hydrogen is coming out, hydrogen is going out, hydrogen is coming out, hydrogen is going out. So these two images are superimposable. The implication is that they are chiral. The implication is that propanoic acid cannot be able to rotate plain polarized light, but from lactic acid can be able to do that, because we have enantiomers that are non-superimposable on each other. We're going to be looking at the criterion for chirality. We just talked about chiral objects having non-superimposable image. Now, very importantly, what will make an object to be achiral is the presence of symmetry. The presence of symmetry will make an object to be achiral. Now, when we talk about symmetry, mathematically, it has its own definition. But for the purpose of this particular course, I'll just define symmetry as either a plane or a line or a point where there's corresponding similar shapes on both sides of that symmetry that we're talking about, or that reference point we're talking about. So when, for example, let's look at something like this. So let's assume that this is a square. Now you can say that there's a symmetry in this square because this side of this square is exactly the same as this particular side. You can say that there's a symmetry on this part because this side of this square is exactly the same with the other side. You can say that there's a symmetry on this part because this side of the square is exactly as the same on that side. I'm just trying to explain to you what symmetry is all about. So presence of symmetry. Now there are three elements of symmetry. We have symmetry axis. Now symmetry axis can also be referred to as line of symmetry. Symmetry axis can also be referred to as line of symmetry. Then we have plane, or you can refer to it as mirror plane. So that's plane of symmetry. Then we can now talk about points, and we can refer to that as inversion. Now these three symmetry elements have their own role to play when it comes to definition of symmetry, and then these three symmetry elements now works with 5 symmetry operations that we're going to be looking at very, very shortly. So there are 5 symmetry operations that work with these 3 elements of symmetry, and I'm going to be starting with the first symmetry operation. What we have in the first symmetry operation is n-fold rotation. And is represented as Cn, where n is an integer. So this actually refers to a rotation of 360 degrees divided by n. N can be 2, n can be 3, n can be 4, n can be 5, and so on and so forth. Now when a compound has a particular number of rotation, for example C2 here, that is when n is 2, is going to be 360 divided by 2, that's going to give us 180 degrees. Now C3 here, when n is equal to 3, is going to be 120 degrees. Now C4 here, when n is equal to 4, is going to be 90 degrees, and so on and so forth. Now when a molecule actually has any form of rotation, n-fold rotation, such that when it rotates in any of these folds, it gives back the original rotation, it means that it has an axis of symmetry. or it has this symmetry operation n-fold rotation. So let's use water as an example. So this is the structure of water. So we have oxygen connected to hydrogen, connected to hydrogen. So this is water. Now, if you rotate water 180 degrees, if you rotate water 180 degrees, it means that first of all, this water is going to come out and then it's now going to go back. So this first coming out is 90 degrees and then going back is 180 degrees. You will now have this hydrogen will now be on this side and then this hydrogen will now be on this side. You are still having the same molecule. So it means that water has a C2 n-fold rotation, because with 180 degrees you are getting exactly the same image. So it means that water is achiral because it has an axis of symmetry. So the element of symmetry being used here is axis of symmetry, also known as line of symmetry. But then let's look at if you turn water 90 degrees, that means what is like this, you turn it 90 degrees. This is what we're not going to have. Our water will now have okay, we now have a wedge bond hydrogen, because one hydrogen is now outside. Then you now have a hash bond hydrogen, but the other one is now at the back. Now this image and this image are not the same. The implication is that water does not have C4 rotation, because what we have here is a 90 degrees movement of water. So it means that water does not have C4 rotation, but water has C2 rotation to give it the exact same image. So that is that about n-fold rotation. Now the second symmetry element we're going to talk about is reflection. And reflection is represented as sigma. And then reflection actually works with the elements of symmetry referred to as plane of symmetry. And we also call that mirror plane. Now, plane of symmetry simply means when there's a plane on the compound that gives it a mirror image, like the two parts between that particular plane is going to give a mirror image that exactly the same. So for easier understanding, let's also use water and let's see what it's like. So this is water, O, and then we have H, Now, if you have a plane here, you know, plane is different from line. This is line. But when we talk about plane is like a flat surface. So if you have a plane that is cutting through this place, okay, let me see if I can draw anything. So this is like a plane that is cutting through this place. So when you are talking about plane, you want to look at something, just any flat surface cutting through this. You find that this side of the molecule, that's the H here, is same thing as this side of the molecule. So since these two mirror images are the same, you can simply say that water has a plane of symmetry. Now, from what you are saying, you can already see that water has a vertical plane of symmetry. Usually, we can represent that as sigma V, a vertical plane of symmetry. Now, another plane of symmetry we can still see in this water is what we refer to as external plane of symmetry. Now, external plane of symmetry simply refers to the plane that occurs when the plane cuts through the molecule. For example, this is a flat drawing, and from what we are seeing already, we can see that this bond, stick bond, is representing this flat surface. Stick bond is representing this flat surface. I told you that the wedge bond means that it is coming out, and the hash bond means that it is going back. So these ones are on this particular surface. So if you have a plane that cuts through this particular surface, that's a plane that is like this, for example, just something that cuts. Let me draw it fully. But it's not cutting only the bond, it's also cutting through the elements. So something that cuts through this completely, what you have at the front is going to be equivalent with what you have at the back, because there's no other molecule probably going outside or any molecule coming outside. Everything is on this surface, so you can cut right through it, and the front will also be reflecting the back. Now, that kind of symmetry is referred to as external plane of symmetry. external plane of symmetry. So anytime you have a structure that just has only stick bond, usually you will find an external plane of symmetry. The implication is that it can never be chiral because a plane of symmetry is present. Let's look at another compound so I can to understand another important part of this. Let's look at xenon tetrafluoride. Now xenon tetrafluoride is XaF4. So this is xenon, and then we have fluorine atom, we have fluorine atom, we have fluorine atom, and we have fluorine atom. So this is xenon tetrachloride. Now if we use a plane on this place, this side is a mirror image of this side. So we have one vertical plane of symmetry. If we use a plane that goes this way, we have two F's here and we have two F's here. This is a mirror image of this particular one. So it means that there's a diagonal plane of symmetry. If we decide to go this way, we'll have fluorine here and we have fluorine here. These two sides are mirror images of this each other. So we can also refer to this as horizontal plane of symmetry. And like I already told you, the moment you have stick bonds all through, it means to also have an external plane of symmetry. So let's count how many plane of symmetry does xenon tetrafluoride has. It has 1, 2, 3, and 4. So we have vertical, diagonal, horizontal, and then the external plane of symmetry is also a vertical plane of symmetry. Now, these ones that are inside are referred to as internal plane of symmetry, while the one that is external is referred to as external plane of symmetry. So both external and this vertical are both vertical, while this is diagonal and this is horizontal. So those are the two symmetry operations that have been taught about so far. So let's go ahead and talk about the remaining three, and then we'll make progress on this particular lecture. Number 3 is going to be inversion. Now, an inversion is represented as I. Now, the symmetry element that works with inversion is the inversion point or point of inversion or center of inversion or inversion center. So that is the symmetry element that works with this particular symmetry operation. Now, what do we mean by inversion or points of inversion or inversion center? What we're talking about is that in that particular molecule, if you take every atom to the opposite side, let that atom relate or superimpose on another atom that is exactly like it. The moment you have a particular center where movements of atoms directly opposite themselves superimpose on an atom that is similar to it, the implication is that that element or that compound has an inversion point or has an inversion center. So for clearer understanding, because I understand that practical based things or examples will help you to understand the concept of these things much more effectively, we are going to be working with 6,1,2-dichloroethane, and then we're going to be working with the trans version of it. So let me draw dichloroethane for you to understand that better. So this is carbon. Since it's 18, we have 2 double bond. Then since it is a cis, you have chlorine, you have hydrogen, you have hydrogen. Now let's move. Obviously, from this point, the center we have here is at the center. So let's move each atom and see if it's going to have the same image on each side. If you move chlorine directly opposite itself, it will be on hydrogen. Hydrogen is not something as chlorine. So the implication is that here it cannot be referred to as an inversion point or a center of inversion in an inversion center. Now, if you move hydrogen from this point to this side, hydrogen is not chlorine and chlorine is not hydrogen. So the implication is that here cannot be referred to as an inversion center for cis-1,2-dichloroethane. How about if I'm not working with trans-1,2-dichloroethane? In trans, what we're going to be having now is that instead of our chlorine to be up, we're going to be having our chlorine down here. We're going to be having our hydrogen down here. Now, if you move your hydrogen to this particular point and you're moving this one here, they are replacing each other. They are same atom. If you move your chlorine here and you move this one another one here, they are replacing each other. They are same atom. So the implication is that this place is going to be a center of inversion for trans 1,2-dichloroethane. Another very good example of this is our benzene ring. So let's look at our benzene ring. So this is our benzene ring, and we have um yeah, we have hydrogen, 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 and then we have hydrogen. Now this is our inversion point. Why is it an inversion point? Because if you move this hydrogen to this point and you move this one here, move this to this point, move this one here, move this to this point, move this to this point, you will still have the same benzene ring. So nothing changed. So the implication is that there's an inversion center here. So any compound that has inversion center or inversion point automatically will be achiral. Simple tip. You already see for yourself that benzene is achiral. One of the reasons is because it has a center of inversion altogether. So the other two symmetry operations, the other one we have improper rotational axis of symmetry, or you can also call it rotation reflection axis of symmetry. Now this is represented by a symbol xn. For the purpose of this particular tutorial, we're not going to be going deep into this because it's going to be quite complex and will not really serve the purpose for which you are doing this tutorial. So you could always request if you need more explanation on this. Now the fifth one, which is very simple, is the identity operation. Now the identity operation is represented as E, and what it simply means is that you are rotating the image by 360 degrees. If you rotate something by 360 degrees, automatically it will get back to where it started from. So identity operation will definitely give you the same image of that particular object, and it's as good as multiplying the object by 1. So what you are having in identity operation, every molecule, every compound has the identity operation. So with this in place, we have been able to look at all of the symmetry operations we have in this particular tutorial. So what we're going to be looking at now is how to identify plane of symmetry. I've already told you before that plane of symmetry simply means, like, plane simply refers to like a flat surface. Plane simply refers to like a flat surface. So we're going to be looking at how to identify planes of symmetry quickly with several examples so that you can grasp how to identify these things and know when an object is chiral and when the object is achiral. So we're going to be looking at the planes of symmetries in these different compounds that were drawn on the board. So we're going to be starting with the first compound. Remember, any compound that has symmetry automatically will be achiral. But when it lacks symmetry and it's in order, then that compound becomes chiral. The implication is that it can be able to rotate plane polarized light. So let's look at this first compound. This is methane. Methane is 1 carbon and then 4 hydrogen. So let us see the planes or symmetries that are present in this compound. Remember, wedge bond means it's coming out from the plane, the hash bond means it's going away from the plane, and then the stick bond means that it is right on the plane. So this particular compound has 6 planes of symmetry. It has 6 planes of symmetry. Now, how do I mean, or what do I mean by that? For example, if you have a plane that is running through your H1, through the C, and then through the H2, what I mean by that is that you're having a plane that is cutting across H1, C, and H2. What you're going to be having on the remaining both sides is H4 and H3. Are you getting the point now? So what you're going to be having on both sides is H4 and H3, and 2 of them are same hydrogen. The implication is that you have a mirror, so that is a plane. Another plane you can have is that you can say, okay, let's have a plane that cuts through H1, C, and H3. The moment you have that plane, a plane that runs through H1, C, and H3. The moment you have that plane, what you're going to be having reflecting on both sides is H2 and H4, and 2 of them are HH. The implication is that there's a plane of symmetry on that. Another plane of symmetry we want to run is, okay, let us cut through this. So remember, you're having this coming forward, this one going backward. You are cutting through this particular plane. So you're going to be cutting through H1, C, and then H4. So you're going to be having a reflection of H3 and H2. Are you getting what I'm saying? Now you're going to be having a reflection of H3 and H2, and since both of them are hydrogen, the implication is that that's a mirror plane. Another thing again you can decide to do is that you can decide I want to cut through H2, C, and H3. Now, since, for example, now look at this. So since our H2 is at this back, our H3 is at the front, and then our carbon is this way. So you can cut through it. The moment you are cutting through it, you're going to be having this H1 at the top, you're going to be having H4 at the bottom. So by implication, these two are going to be mirror images, and you're going to be having H2, a plane of symmetry running through H2, C, and then H3. So these two will be mirror images, and that's going to give you a plane of symmetry. You could also decide that you want to do H2, carbon, and then H4. So you're going to be having H2, carbon, and H4. You're going to be having hydrogen 1 and hydrogen 3, and H1 and H3 being mirror images of each other. The implication is that you're going to be having a mirror plane of H2 through carbon and through H4. So the mirror is what? H1 and H3, and since both of them are hydrogen, it means that this is a confirmed plane of symmetry. Now you could also decide you want to do your plane of symmetry between H3, carbon, and H4. So the mirror image now be between H1 and H2. That mirror image is already make this one like its own plane of symmetry. So this is H3 to carbon to H4. So how many planes of symmetry have we counted already? We have 1, 2, 3, 4, 5, 6. So what we have here is 6 planes of symmetry. So let's go to the next one now. This carbon has bromine, chlorine, and hydrogen. And the question you ask yourself is, does it have a plane of symmetry? Now let us see that. If you cut through hydrogen, carbon, and bromine, you have bromine and chlorine left. These two are not mirror images, so this is not a plane of symmetry. If you go through hydrogen, carbon, and bromine and chlorine are not same thing, so this is not a plane of symmetry. But if you go through hydrogen, carbon, and chlorine, that's you are cutting through this way. So what we have is hydrogen, carbon, and chlorine are cutting through this way. You're going to be having bromine at the front, and you're going to be having bromine at the back, as you can already see on this bond, and two of them are same. So the implication is that you're having a mirror image of bromine. So we have a plane of symmetry that cuts across hydrogen, carbon, and chloride to give a mirror image of bromine and bromine. So the implication is that this particular compound is also achiral. So let's just put that here. This is achiral, and this one we said it has 6 planes of symmetry, and this one it has 1 plane of symmetry. Now we can't have an external plane of symmetry here, because when you have an external plane of symmetry, the only thing that we cut is H, carbon, and Cl. It's not going to cut through bromine, it's not going to cut through this bromine, because these two are not on the plane of the paper. While one is going backward, the other one is coming forward. Are we making sense now? So let us look at this second compound, so you understand the third compound, so you understand what we're talking about very appropriately. Now this is carbon attached to hydrogen, fluorine, bromine, and chlorine. So let us see if we are going to find any plane of symmetry. Now if you have a bond that is a plane that is cutting between hydrogen, carbon, and fluorine, you have chloride and bromide, chlorine and bromine, that's not same image. So the implication is that that's not a plane of symmetry. Hydrogen, chlorine, carbon, and bromine, we are going to have chlorine and fluorine. These two are not same elements, so the implication is that that's not a mirror image and it doesn't have a plane of symmetry on that regard. Hydrogen, carbon, and chlorine, we are going to have bromine and fluorine, so there's no mirror image. The implication is that this compound has no plane of symmetry, and when it doesn't have a plane of symmetry, we simply say that this compound is chiral, so it has 0 plane of symmetry. Now for you to just take note, whenever you have a carbon that has 4 different substituents attached to it, that carbon or that compound is usually a chiral compound. So it's very important you take note of that. Now let us go to this particular compound. Here we have carbon double bonded to each other, and then we have hydrogen. This is an 18 molecule. Now let us see the number of planes of symmetry we have there. First of all, we have a vertical plane of symmetry. Now we have hydrogen, carbon, carbon, hydrogen. So these two places are mirror images of each other. So we have 1 vertical plane of symmetry. How about through this place? So I have a horizontal plane of symmetry, because hydrogen is mirror image of hydrogen. Hydrogen is mirror image of hydrogen. So this is also going to have a horizontal plane of symmetry. Another plane of symmetry that is very important, like I mentioned, since all of them are on this particular plane, we can slice through it. We can slice through it. So at the front side will be reflection of the back side. So the implication is that this will also have an external plane of symmetry. So the implication is that here we have three planes of symmetry, one vertical, one horizontal, and one an external plane of symmetry. And by implication, this molecule is a chiral. So let's look at this particular molecule also. So this is carbon, carbon, bromine, bromine, hydrogen, hydrogen. Now, what planes of symmetry do we have here? This is not a plane of symmetry. The implication is because bromine is not same as hydrogen, and hydrogen is not same as bromine. So here cannot be a plane of symmetry. Same way, here cannot be a plane of symmetry because bromine is not same as hydrogen, and hydrogen is not same as bromine. But we have one plane of symmetry that is here. Because all of these bonds are on a flat surface, the implication is that we must have an external plane of symmetry that is slicing through it. So at the front, we'll be reflecting the back. So by implication, we have one external plane of symmetry, and this is going to be a chiral. Now let's look at this particular one also. We don't have a plane of symmetry here because bromine is not hydroxyl group and hydrogen is not chlorine. We don't have a plane of symmetry here because bromine is not hydrogen and hydroxyl group is not chlorine. But we have one plane of symmetry because this is on a flat surface, and that plane of symmetry is external plane of symmetry that's going to slice through it. So it has one external plane of symmetry. By implication, this molecule is a chiral. So let's look at this particular molecule also. What planes of symmetry do we have here? First of all, we have a horizontal plane of symmetry. The implication is because we have a methyl group here that's also reflecting another methyl group here. So this is a horizontal plane of symmetry. We cannot have anyone here because we don't have any mirror image of this on this particular side. But then, because all of the bonds are on the flat surface, there's one plane of symmetry we have there. You're already guessing it, right? An external plane of symmetry. So the implication is that we have two planes of symmetry here. One is horizontal, and we have the other one as the external plane of symmetry. So the implication is that this molecule is going to be a chiral. So let's look at the last one. This particular one, before we go to further examples and begin to look at ring structures. Now, this particular compound happens to have C double bonded to C double bonded to C. Now I'm going to tell you the name of this kind of compounds as we progress in this particular lecture. You realize that we have methyl group on the stick bonds, and then we're having on this particular side we have dash bond and wedge bond. The implication is that all of the bonds are not on the same plane because we have the one that is coming forward and we have the one that is going backward. So the implication is that first of all, we are not going to have an external plane of symmetry because once you are cutting it this way, it will not cut through this hydrogen, it will not cut this hydrogen because these ones are coming out, the other one is going backwards. So what we're going to be having here is that first of all, we will have we have a plane of symmetry that is vertical. Now let me explain the vertical I'm talking about. When you cut through this, it is going to cut through this bond, this, leaving behind only the hydrogen and this hydrogen. Now these two are mirror images, so the implication is that we have one mirror plane that is what? Vertical. Now another way again we can go to work on it is that we can work on horizontal plane. Now if you cut this horizontally, remember that what we have here is hydrogen, and then you are cutting it horizontally. So you're going to be cutting through both the hydrogen at the front and the hydrogen at the back, and then you're going to be cutting through this carbon, and carbon. So what you'll be left with is methyl group and methyl group, and since two of them are mirror images of each other, it means that you have another plane of symmetry here. So we have a plane of symmetry on this basis, and we have a plane of symmetry that is vertical, so horizontal and vertical. So we have two planes of symmetry, but none of them is external. The reason is because these two are not on the same plane such that it will be able to cut through all of them. So we have two planes of symmetry, horizontal and vertical, and it's going to make this molecule to be a chiral. So let's look at more examples. So we have some cycloalkanes we can use to understand identify planes of symmetry. So let's look at this very one here. So this cycloalkane we have here, we have a bond, a wedge bond that connects a methyl group, and a stick bond, a hash bond that connects a methyl group. Now, can we call this a plane of symmetry? We cannot call this a plane of symmetry. The reason is because why this one is going forward outside, this one is going backwards, so they are not mirror images of each other. What you're having here and what you're having here are not mirror images of each other because of the distinctiveness in the bond. Assuming this bond here happens to be a wedge bond, it means that you can have them as what? Mirror images. So this does not have a plane of symmetry, and by implication, it is a chiral compound. It is a chiral compound. So let's look at the second one. Now, does it have a plane of symmetry? Yes, it does have a plane of symmetry, and the plane of symmetry we have here is this plane of symmetry, because this side is mirror image of this particular side. So this is a plane of symmetry, and by implication, this compound is a chiral. This compound is a chiral. What about this particular compound? How many planes of symmetry do we have? Now, this is a plane of symmetry. So this side is same as this side, so it's a plane of symmetry. We also have a second plane of symmetry because this side is a mirror image of the other side. So the implication is that this is an achiral compound. How about this particular compound? This is methyl group here and this is ethyl group here, but here is a plane of symmetry such that here is equal to this. But we don't have a plane of symmetry this way because while we are having a methyl group here, this is an ethyl group. So the implication is that this one has only one plane of symmetry, while this has two planes of symmetry. So how about this one? We have a plane of symmetry here. We have a plane of symmetry here because this is going backwards and these two are coming forward, so they are mirror images of each other. Now you cannot have a plane of symmetry this way. The question is because this is a wedge bond coming forward and this is a hash bond going backwards, so they are not mirror images of each other. And if you go this way, these two are not mirror images of each other, but these two that are coming forward are mirror images of each other. So the implication is that you have just one plane or symmetry on this particular compound. How about this compound? All of them are coming forward, so you have a plane of symmetry that divides it into these two, you have a plane of symmetry that divides it into these two, and then you have a plane of symmetry that divides it into these two. So the implication is that we have three planes of symmetry, and all of these compounds that have planes of symmetry are achiral compounds. So I think with this very clearly explained examples, you should be able to identify planes of symmetries in any particular compound you encounter. So we're going to be working on molecular geometry and then we'll make progress. So let's look at some molecular geometry shapes and then see some very important definitions that can help you understand a few things. So we have different shapes or geometry of shapes. We have linear, we have trigonal planar, we have bend shape, also known as V-shaped, and you can also refer to it as angular, and then we have the tetrahedral shape, we have the octahedral shape, we have the square planar, and we have the trigonal pyramidal. So let's start with the linear shape. Now, linear shape is when you have, let's say, a bond that is connected on a straight line. So an example is carbon 4, like this is carbon, double bonded to oxygen, double bonded to hydrogen, and it's on a straight line. So we refer to that as linear shape. Another example can be nitrogen 4 oxide, that's NO2. So it has an angle of 180 degrees, an angle of 180 degrees because on a straight line. So the next one we're talking about is trigonal planar, where we have a molecule bonded together in such a way that it forms a triangle, but then the bonds are on a plane. So that's why we refer to it as trigonal planar. It's different from trigonal pyramidal. When we get there, you understand better. So this is on a plane, and the bond angle between any of the two, any of the bonds is 120 degrees. Then we have the angular shape, which is also referred to as bend shape, or also referred to it as V shape. And the angle of between the two bonds is 105 degrees Celsius. An example is water, that is H2O. So that's what we have there in that particular structure. Another shape we have is tetrahedral. In tetrahedral, we have a carbon that is or an atom that is bonded to 4 different atoms. So here we have methane, where that's CH4, where we have a carbon that is bonded to 4 different hydrogens. So the bond angle between any of the bonds is 109.45 degrees. So this is a tetrahedral shape having 4 sides. Then the next one we have is octahedral shapes. Now in octahedral, we have 8 bonds. Let me see if I can be able to sketch the structure of a tetrahedron so that you can understand basically what we have here. So let's see if that is obtainable. Yeah. Let's see if I can be able to sketch the structure of an octahedron. Okay. Yeah. So we can have Something that is coming, sorry, something that's coming this way and then that way and that way. Okay, I'm just trying very hard to be able to sketch something like a tetrahedron, but if we want to look up that image probably online. Now, in this particular tetrahedron, we have 8 different sides: 1, 2, 3, 4 outside, and then at the back we have 1, 2, 3, 4. I don't know if you get what I'm saying. So this what we're having here is just like the front part of it. I was trying to sketch the back using these dotted lines. So at the back also, when we have 1, 2, 3, 4 at the front, at the back also we also have 1, 2, 3, 4 behind it. So those are 8 sides, and then working with the 8 bonds. So that's what the kind of structure you can have from something like sulfur hexafluoride. So you have 6 atoms of sulfur, but then you're having like 8 sides. So that's exactly why we're referring to it as octahedral. So it has 8 bonds that are working together, and the bond angle is 90 degrees. So another one again we have is trigonal pyramida. In trigonal pyramida, we have a shape that has something like a triangular base, but like I told you, this one is on a plane, this one is not on a plane, because we are having a wedge bond and also a corresponding hash bond. So this is trigonal pyramida, and the angle between the 2 bonds is either between greater than 90 degrees but less than 109.5 degrees. So the last one we're going to be talking about is the square planar. Square planar simply means you have 4 different bonds in a square shape or in a square arrangement in such a way that the angle between all of them is 90 degrees. An example of square planar bond, where you find square planar bond, is xenon tetrafluoride. Now, one very important thing you have to notice is that any of these shapes or any of these geometrical shapes or arrangements that is planar we usually have what we have already explained, which is the external plane of symmetry, because you can cut through it. For example, this carbon is linear, you can cut through it. It means it has an external plane of symmetry. This particular one, you can cut through it. It means it has an external plane of symmetry. So that's NH3. So this particular one, it has an external plane of symmetry. You can cut through it. So this square planar, you can cut through it. So the implication is that any structure that is planar will always have an external plane of symmetry, and the implication is that planar structures can never be chiral, because the plane of symmetry automatically has already cancelled out the criterion for planarity. But then when we have shapes that are tetrahedral, we have shapes that are octahedral, or we have shapes that are trigonal pyramidal, with appropriate substitution and arrangement, it is most likely you can avoid having any form of plane or symmetry. The implication is that for compounds that are either tetrahedral, octahedral, trigonal, pyramidal, that also have flat or planar structures, that is where you can go to find chiral compounds, and then that is if they are properly substituted and if they are properly arranged in the particular structure. But any structure that is planar, that does not have any wedge bond or hash bond, that structure will never be chiral, because there will always be an external plane of symmetry. So let's look at the meaning of disymmetric and asymmetric as we make progress in this particular lecture. We're going to talk about disymmetric compounds and then asymmetric compounds. Now, when we talk about disymmetric simply means that the compounds are lacking in 2 elements of symmetry. Okay, let me write that down here. So for disymmetric, we are having an element or a compound, that lacks 2 elements of symmetry. That is the plane of symmetry, and then we have the points of inversion or the inversion center or the inversion point. Now, a compound that is disymmetric has the capacity of being chiral. A compound that is disymmetric has the capacity of being chiral. So the moment you lack plane symmetry and you lack points of inversion, automatically you become a chiral compound. But then when we talk about asymmetric simply means that the compound lacks 3 elements of symmetry. We have the plane, as we have here, we have the points, and then we have the axis of symmetry. So this one lacks 3 and this one lacks 2. Now, once you've already lacked 2, or any compound already lacks plane of symmetry and points of inversion, it must be chiral. But then it does not necessarily need to lack the 3 of them for it to be chiral. Now, this is what it implies. It implies that asymmetric compounds are always chiral, but chiral compounds are not always asymmetric. So why exactly do we have that? Asymmetric compounds are already lacking the three elements of symmetry, so they are always chiral. But chiral compounds are not always asymmetric. Okay. The reason is because chiral compounds could also be disymmetric. And like I mentioned, the moment you lack plane of symmetry and point of inversion center, you automatically become chiral. So asymmetric compounds will always be chiral, but chiral compounds will not always be asymmetric because some chiral compounds can be disymmetric. So carbon, asymmetric carbon, like when we have a carbon having four different substituents, can also exhibit chirality. And apart from compounds that has carbon, compounds that has things like sulfur, compounds that have phosphorus, compound that has nitrogen can also show some level of chirality if the substituents and other things are put in order.